So in these notes we want to deal with an introduction to vectors. Deal with vectors here. And when we define a vector, basically we're worried about two things. We have to have a length, which we also call magnitude. So you hear both of these words, they're interchangeable. And the other thing we worry about, other than the length, is we also worry about the direction of a vector. So a vector is defined in terms of its length and its direction. So some examples of this, let's just put some points here on some axes. These just, we're going to do x and y. So we're going to work in 2 dimensions because it's easier to draw. You could do this in 3 or as many dimensions as you want, really. I'm going to put some points here. Let's say I want to have at least 3 tick marks here, at least 4 in the y direction. Let's say this is x, that's y, a couple here, at least 1 there. I'm going to put a point at 1, 2. I'm going to call that point A. I'm going to put a point at 3, 5. I guess I want 1 more there. I'm going to put a point there at 3, 5. Call that B. I'm going to put a point at -2, 1. Call that C. And I'm going to put a point at 0, 4. Call that D. And 2 more. We want to put 0, 1. Call that E. And then a point at 3, -1. And call that. So a bunch of points that we'll refer to with various vectors here. And sort of a standard way to do a vector is you have an initial point, say A, in this case, whoops. So we have initial point A, and we go to a terminal point B. So this vector from A to B, we're going to call that the vector AB, and typically we're going to put some kind of arrow over this. I'll sometimes do sort of a arrow left or right, and then I have sort of just the 1/2 of sort of the arrow part on there. Sometimes people will write this AB and put in like an actual, whoops, that didn't turn out very well. Put an actual AB and then do an arrow that's still not doing very well. Let's draw the arrow first. Arrow like that, and do AB. So it's just different notation for the same thing here. Okay, so that's AB. Now, something to note here is that if you start at C and go to D here, this is the vector CD here. Well, if you go from C to D, you go over 2 and up 1, 2, 3. From A to B, you go over 2 and up 1, 2, 3. So it turns out that these two vectors, AB and CD, that they're in the same direction. They're also going to have the same length or magnitude because they're really the same vector. And so this is maybe one of the weird things about vectors here, is that we're going to say that AB and CD, these are actually the same vector. So even though they're in different spots, we're still going to call these the same vector here. And essentially that means that vectors are an equivalence relation, whatever that means, on these sort of arrows here that we would have in the plane or in 3-dimensional space or whatever dimensions you're working in. Okay, now we can describe these. So when we think about this as really going 2 over and 3 up, you can actually sort of come up with this mathematically, and you can say AB here, well, it's going to be its terminal point. It's the point it ends at, so that's going to be B is 3, 5. And then we're going to subtract its initial point A, which is 1, 2. And when we do the subtraction, we're going to do this coordinate-wise. It's going to be 3 minus 1 and 5 minus 2. And when I write the vector, I'm going to tend to switch to an angle bracket notation instead of parentheses for points. There's all sorts of different notations that you may see here, though. So that I do the 3 minus 1, and then the 5 minus 2. So that gives me a 2, 3. So AB is really the vector 2, 3. And you can see when we say A, B, and C D are the same vector. CD, D is the point 0, 4. C is the point -2, 1. And so this is going to give me 0, minus -2, and then 4 minus 1. It's going to give me the same 2, 3. So those work out to be the same vector. Now, another vector we've got sitting around here, this is EF here. This one, instead of going over 2 and up 3, we go sort of over 3 and then down 2. So it's a different vector here. It points clearly in a different direction. It will end up having the same length, though. So EF, if we want to do this, we're going to take the second letter, that's the terminal point, F, that's 1, 2, 3, -1, and subtract the initial point E, which is 0, 1 here. And you'll get 3 minus 0, and then -1 minus 1. So it should give you 3, -2. Okay, so that's all in 2 dimensions. You can do this in 3 dimensions as well. I'm not going to draw this because the drawings get a little confusing and hard to figure out what's going on here. But let's say we want to do the vector here with the initial point. I'm going to choose 3, -1, 4, somewhat randomly. Note that's a 3-dimensional point, or a point in 3-dimensional space. And the terminal point, that is the end part of the vector. So initial point is 3, -1, 4, terminal point is 0, 2, -1. This vector is, well, what we do, we're going to do, it's terminal minus initial, component-wise, 0 minus 3, 2 minus -1, and then -1 minus 4. That gives us -3, 3, -5. So we can sort of write down a vector like this. There's other ways to write this here, and so we'll get some other notations. I'm just going to write that vector -3, 3, -5 a couple other ways, a few other ways actually. What we'll see here is, so we'll do -3, 3, -5. And sometimes you'll have people write these with maybe just parentheses instead of these angle brackets. You might even see square brackets, perhaps, here. So these are all really just changing the brackets. Not really any difference here. A couple ways you might view this that's somehow substantively a little bit different. This isn't going to look that, but I'm going to drop the commas. Now this looks pretty much exactly like what I wrote here, except I don't have the commas there. But now I'm thinking of this as really a 1×3 matrix. And I'm going to maybe think of this as a row vector if you're used to working with matrices. Sometimes people also write this as a column vector. You could do -3, 3, -5, like that. So that would be a column vector. Here. So there's a couple different ways. Another way that's maybe a little bit different in feel here, so we're going to introduce some vectors. So we're going to call them I, and we're going to let I be the vector 1, 0, 0. J is the vector 0, 1, 0. And let's scroll down a little bit. Oh, no more space on this page. So let's let K be the vector 0, 0, 1. And then it turns out that our vector -3, 3, -5, using some rules of vector sort of arithmetic or algebra that we'll do in a bit, that this works out to be -3i plus 3j minus 5k. So effectively all I'm doing here is writing the I, j, k, and the first component, the -3, goes with the I. The second component, the 3, goes with multiplied by the j. -5 gets multiplied by the k. So we'll learn sort of how to do this a little bit different way. These I, j, and k are called standard basis vectors here. And sometimes that's more advantageous. Particularly, this notation is really nice if you had a bunch of zeros here. Imagine you had a much larger, well, even in 3 dimensions, you have 2 of these being 0. So if you had something like 0, 0, 2, you could just write this as 2k. There. So it's sort of a little bit shorter hand than even the 0, 0, 2 there. It can be useful. I'll also point out one thing I'm doing here is I'm running these arrows over the I, j, k to indicate that those are actually vectors here. Okay. That's our vector, just sort of getting some notations down you may see in other places. Another sort of amount of bookkeeping here. So we're going to talk about the 0 vector. This is more a notational thing here. So the 0 vector, well, it's the vector of all zeros. So in 3-dimensional space, this 0 vector, what I'm going to do is I'm going to write it as 0, but then I'm going to put sort of this vector symbol over it. So when I see 0 with a vector symbol over it, that's a vector of all zeros. So a note here, and this is a common mistake people make here, is it's sometimes people write 0, 0, 0 equals just 0. Now, I may know what you mean if this makes sense in context, but note these are actually not equal here. Note that symbol a little. So not equal. Because what happens is the 0, 0, 0, this is a vector, and the 0, that's just a number, which we're going to start referring to as a scalar. So that's just a number there. And we can't have a vector equal to a scalar. So if you put the arrow on top, then you would actually get the 0 vector. Something else that's important to know here is when I just write the 0 vector like this, we really need to know what sort of dimension or what kind of space we're working in. So if we're in R3 here, then the 0 vector really is 0, 0, 0. But if we're in, say, R2, then the 0 vector is just 0, 0. Or if we're in R5, say, then the 0 vector is a vector of 5 zeros. 1, 2, 3, 4, 5. So this use sort of the same notation for each of these, and it's just hopefully clear by context which one you mean. Sometimes you might dress that notation up if it was not clear for some reason. Put a 2, 3, or 5 on it. Okay. Now, with the vectors, we said we had a magnitude and direction. We're not really going to talk about the direction here a whole lot, but we can talk about how to calculate the magnitude or length. So we can do a magnitude or the length here. And it turns out that the length of vector A, B, C, we're going to use essentially our distance formula. Square root of a squared plus b squared plus c squared. So that's our length of a vector here. Now, when we write this, so we get the length of a, b, c, this is a lot to write out, so we'll sometimes shorthand this as really we've got sort of an absolute value notation to mean sort of length distance there. You may also see people do a double bar notation here as well. So I'm going to tend to use just a single bar, but sometimes people use double bars to say magnitude of a vector. Okay, so let's do an example. Just this calculation. So let's find the length. So find the length of the vector 2, 0, -3. And what you get is the magnitude of 2, 0, -3. So that's just square root of 2 squared plus 0 squared plus -3 squared. Don't really need the negative because when you square it, it's going to go away. And that gives you 4 plus 0 plus -3 squared is 9. we just end up with square root of 13 as our length. Oh, so we can do this a little bit differently as well. Another example. So we can say find the length of the vector with initial point. I'm just going to put a point down here. How about 3, 5, 2? And terminal point 4, 2, 6. Okay, so if I wanted to draw this, all I'd really do is put a point somewhere on my page. Say that's 3, 5, 2. Put a point somewhere else on my page. Say that's 4, 2, 6. And then I'm just going to draw the sort of line between them and put an arrow where I start at 3, 5, 2 and I go to 4, 2, 6 here. I'm not really trying to put these in space in some coordinate system. Depending on how you rotate things, it's going to look basically the same anyway. Here. I don't need to do that picture for the calculation, but sometimes it helps us think about what's going on. And so what I'm going to get, well, let's give this a name. So let's call this a vector. How about V for vector? And then I'll put the arrow over it to denote that that's a vector. Well, then the magnitude of V, well, this is the magnitude. What is the vector? Well, I have to subtract these. So I get 4 minus 3. That's the x-coordinate. The second component is 2 minus 5. Third component is 6 minus 2. So I get the magnitude of the vector 1, negative 3, 4. And what that works out to be is a square root of 1 squared plus negative 3 squared plus 4 squared, square root of 1 plus 9 plus 16. It works out to be square root of 26. So we can calculate a length of a vector given the initial point and the terminal point as well. One thing you might note here is that the length of the vector with initial point, how about call this x1, y1, z1, and terminal point x2, y2, z2. Well, what's this? Well, it should just be the square root of, I'm going to take the sort of first component of the vector, so it's going to be the x2 minus the x1 squared, plus the second component of the vector, y2 minus y1, but then I have to square that, plus the third component, z2 minus z1, square that, so we get some formula here. But note that this is the same thing as the distance between the points x1, y1, z1, and x2, y2, z2. So really that distance formula we did for points really is the same thing as magnitude of a vector if we look at it in the right way. Okay. Now we want to start doing some operations with vectors. So we can do vector addition. And what's going to happen here, well, there's going to be sort of two ways to do this. One is visually. So if we have a vector u, I'm going to put my sort of tail or my initial point at the origin here. And then I've got a, whoops, there's u, and then let's just draw some vector v here. So we've got two vectors u and v. if I want to do u plus v, what I do is I take v, if I'm going to do u plus v, I take v and I just sort of copy it over here. So I can do a copy of v. Again, the location of the vector doesn't matter as long as I have the same direction and magnitude. So that's v as well. And then what I get, let's do this, how about in green here, is that then this vector, where I sort of go out u and then I go out v, that's actually u plus v here. There's some sort of geometric thing. These look like they're perpendicular. That's just random based on the vectors I chose. So this would work for any vectors at all. Oops. Okay, so now the sort of calculational way we can do this, I'm going to write this out for 3 dimensional sort of setup. You could do this for other dimensions as well. Is that if I take a vector u1, u2, u3, note I'm doing my notation a little bit differently than I did up here. So up here, I did x, y, z, all with 1s for the first point, x, y, z, all with 2s for the second point. I'm going to write this up a little bit differently, where I'm going to say my first vector is u. Let's just call this u. I'm going to write it all with u's and then do 1 for the first component, 2 for the second component, 3 for the third component. And let's do v, and I would write as v1, v2, v3. One thing I'll note about the way I write my u's and v's here, the u's always have these little tails here. So that's how I tell a u and a v. Sometimes I get a little sloppy and my v's get a little rounded, but if I don't see the tail, I know that's supposed to be a v. Sometimes it's nice to have little handwriting, things like that, so you can not get confused by your own handwriting. And then what we get is that in this case, u plus v, all that happens is we add component-wise. So we get u1 plus v1. Second component is going to be u2 plus v2. Third component will be u3 plus v3. So we can have a sort of arithmetic rule for vector addition here, and there's sort of a geometric rule as well. Now we can do scalar multiplication, addition. Scalar multiplication as well. And what this is going to be is I'm going to take a scalar. Note I'm not going to write a vector with this. I think if there's just a single number and multiply this by a vector. Make my u, that's supposed to be 1, 2, 3. And there's a question of what should I get? Well, sort of the algebraic thing is actually what happens is k multiplies by each component. So I get k times u1, k times u2, k times u3. So this k sort of shows up in each component 3 times in this case. Sort of graphically, just a sense of what's going on. But if I have a vector u, I guess this is really in 2 dimensions. Here, so if that's u, if I want to build 2u, what I do is I make another copy of u here, and then if I go sort of all the way through here, then that whole thing is 2 times u. So I'm just doubling the length. I'm multiplying the length of u by k, and then having u point in the same direction still. An important sort of special case of this is that if I want to go, I'll do this kind of turquoise here, if I take u and I go in the same length but in the exact opposite direction here, we didn't get quite the same length there, let's extend that out a bit, then that's negative u. So if I multiply by -1, it takes my vector and just points it in the opposite direction, sort of 180 degrees, I'd say, in the plane, but something else will work in 3-dimensional space. From that, we could just say negative of u1, u2, u3, just the vector where I do the opposite of each of the coordinates, negative u1, negative u2, negative u3. You could also put this together where if you want to do u minus v, now if you think about this, this should be a subtraction of vectors. It should be u plus -1 times v, which should be So we're going to do u1, u2, u3, plus, if I distribute the -1 to a vector v1, v2, v3, I'll get negative v1, negative v2, negative v3, and when I'm done, my u minus v turns out to be u1 minus v1, u2 minus v2, and u3 minus v3. So instead of adding component-wise, I subtract. So maybe what you would have guessed anyway. So you can actually write that subtraction in terms of addition by a negative, sort of use the scalar multiplication here. Okay. Now, there's a whole slew of vector properties. Here. I'm going to just write a whole bunch of these things. So one thing, if you go back to our rules, generally these are really easy to show. Here, particularly if you know you're working in, say, three-dimensional space or three-dimensional vectors. We have u plus v. I can switch the order on addition. So this is addition is commutative, would be the word. Here. So we'll write that property down. Another property we'll have, you'll write down commutative. Here. Another property is that if I do u plus the vector v plus w, that's going to be the same thing as doing u plus v first and then adding w. So this is saying add v plus w first, then add u. Same thing as add u plus v first and then add w. And this property, we've seen before, is called associative. Okay, and then there's a whole bunch of other properties we'll get. Some of these have names, but I'm not going to worry about them in this context. If I do u plus the way I describe negative u, this is really u minus u, what I actually get always is a zero vector. Another one, if I do u plus a zero vector, this is the same thing as a zero vector plus u by commutativity up here, but both times I get u. So if I take u and I add 0 to it, I get u, but not just 0, it's a zero vector because u is a vector. There's another one where if I take a to be a scalar, and then multiply this by u plus v, turn out this should distribute. So you actually get a times u plus a times v. I can distribute sort of a scalar addition multiplied by a vector as well. This would give me sort of this u is going to distribute to the a and b. It would be a times u. Whoops, not a vector on the a. So this is going to be a times u plus b times u. So there's 3, 4, we're up to 6 properties here. Let's keep writing these down. We could get another property. We have a sort of associative property where if I let a and b be scalars here, so I have a scalar times a vector, and I'm saying take this b times u first, then take that result and scale by a. But that's going to be the same thing as doing a times b. First, multiply the numbers, and then scale the vector. There's a 7th property. We can pick another property, where if I take a scalar 1, multiply that by u, that should give me u. 1 times anything should be the original thing. That works for vectors as well. Let's see, we could do 0 times u. 0 times anything, that should give me 0, but now I have to think about, do I want 0 scalar or 0 vector? I'm taking a scalar times a vector, that should give me a 0 vector. There. You could also do a scalar times a 0 vector, that will also give you a 0 vector. And a couple other things, maybe I've just been using this already, is that if I take a scalar times a vector, this is a vector. So whatever that is, take any scalar times a vector, I will get a vector back. So 0 times u has to be a vector. So it's 0, but it's the 0 vector. And another property is if I add 2 vectors, this is a vector. So these last two are added for sort of theoretical reasons. But you get a whole bunch of different properties of vectors. You could do examples of this. The idea is you'll probably work with these enough where you'll kind of internalize a lot of these and not really think about them, but the properties are there. And sort of the theoretical context here, so you can actually think about, if you take this whole box, you can actually slim this down a bit. You don't really need all these properties, some imply others. But this gives you, sort of, you have any objects that obey these relations. They don't have to be vectors. Sometimes you could let your vectors be functions and define addition in some way, and if somehow the way you define that addition and multiplication by scalar work out, that means that you have a vector space. So if you've heard this word vector space, there's some properties a vector space has to satisfy, and there's something like these. It might be a little bit, sometimes you could get rid of some of these and prove them from the others here, but these all would be true for a vector space. So don't really need to worry about that in this class. We may have seen that before. Last bit here, I'll talk about unit vectors. So what we'll get is just a really simple definition where a unit vector is a vector with magnitude 1. So 1 sometimes is referred to as a unit, but a unit vector is a vector with magnitude 1. So we can ask questions where is the vector 2/3, negative 2/3, 1/3 a unit vector? So really what you need to do is just find the magnitude of this. And the formula will give you a square root. And we're going to do 2/3 squared plus negative 2/3 squared plus 1/3 squared. That's square root of 4/9 plus 4/9 plus 1/9. So again, the negative squared gives us a positive. Go back here a bit. Oops. So then that's the square root of, if I add these together, I get 4 plus 4 is 8, plus 1 is 9/9. So that's square root of 1, which is 1. So we got a magnitude of 1, and so that means that, yes, our original vector, the 2/3, negative 2/3, 1/3, is a unit vector. Now an example that's not a unit vector, probably giving away the punchline there, but we could look at is 2/5, 3/5, negative 1/5. A unit vector. Note, if I'm going to have a unit vector, each of these components has to be at most 1, because if one was bigger than 1, that square would be bigger than 1, and the magnitude just could not be 1. So I'm going to take the magnitude, 2/5, 3/5, negative 1/5, square root of 2/5 squared plus 3/5 squared plus negative 1/5 squared. That's a square root of 4/25 plus 9/25 plus 1/25. I add those up. 4 plus 9 is 13, plus 1 is 14/25. That's not 1. If you wanted to simplify this, the square root of 25 is 5. You could write this as square root of 14 over 5. In any case, it's not 1 here. And so no 2/5, 3/5, negative 1/5 is not a unit vector. Okay. Now, there's some unit vectors that we've mentioned already that we should talk about. And these are the standard unit vectors. And so these were the I, j, and k. So I, this is the vector 1, 0, 0. Now how do I know this is a unit vector? Well, if you do the magnitude of I, it's the square root of 1 squared plus 0 squared plus 0 squared square root of 1 plus 0 plus 0 is the square root of 1, which is just 1. So that works out much more nicely. And similarly, j, again, was 0, 1, 0. Could run through the same calculation here. For the magnitude of j, you'd get 1. You just get a 0 squared plus 1 squared, but you'll get the same answer in the end. And k is 0, 0, 1. A really ugly one there. Okay. So we've got those here. Now, one more thing we might want to be able to do here with the unit vectors, and that's what we can say is that for any vector v, as long as that v is not the 0 vector, so any vector that's not the 0 vector, it turns out that if I take v and then I multiply by, divide by the magnitude of v, note this is really 1 over the magnitude of v times v. So note this is a scalar times a vector. So magnitude of v is a number, so we're taking a scalar times a vector. So we're just scaling v. So this should be in the same direction as v. And it'll turn out that this will always be a unit vector pointing in the direction of v. And this will be a thing that will be useful later on. And really the idea here is, can you convince yourself that v over magnitude v is a unit vector? Well, if I do the magnitude of v over the magnitude of v, now there's some rules with magnitudes, but what I'm going to do is I'm going to split this up, 1 over the magnitude of v times v, and then if I have a scalar times a vector, this might take some convincing, but I can essentially factor out of the square root this 1 over magnitude of v. And then I'm left with, inside of the magnitude, just v. So this step here you need to convince yourself of. But then I just get magnitude v over magnitude v. I do in fact get 1 there. And because this is a scalar multiple of v, this is a unit vector in the same direction as v. Oh, one other thing here to note, maybe that property that we're using, maybe we should write that up separately, is I'm saying that a times the magnitude of v, or sorry, a times v, and I take the magnitude, this is a times magnitude of v. Note here we're using the same symbol twice. Here a is a scalar, so your bars mean that this is an absolute value of a scalar. And this one, we have a vector inside, so this is a magnitude of a vector. So this is something that's nice to get used to in sort of mathematics here. It's maybe a bit confusing at first, but we're using the same symbols to mean two different things, and even in the same problem. Okay, so last bit here, let's find a unit vector. And this is again a common thing we'll do. In the direction of 3, negative 1, negative 2. Okay, so what I'm going to do is I'm going to say u for my unit vector. What I'm going to do is I'm going to take my original vector. I can think that really is a v. I really need to name it though. I'm going to take my vector 3, negative 1, negative 2. I'm just going to divide by the magnitude of 3, negative 1, negative 2. Vertical bar there. And so this is 3, negative 1, negative 2 divided by the square root of 3 squared plus negative 1 squared plus negative 2 squared. That's 3, negative 1, negative 2 over the square root of 9 plus 1 plus 4. So I get 3, negative 1, negative 2 divided by the square root of 9 plus 1 is 10 plus 4 is 14. And now when I have this scalar on the bottom, I could say this is 1 over square root of 14 times this vector. Turns out, if you work that through, I really just divide component-wise. 3 over square root of 14, negative 1 over square root of 14, and then negative 2 over square root of 14. So this is your unit vector in the same direction as 3, -1, -2. And that's going to end our slides here.